Ever wondered how it's like studying computer science at Oxford? Hello, I'm Oscar. I'm currently a final year studying computer science at University of Oxford, and today I'm delighted to share what I think is the most interesting topic I learned here. Well, believe it or not, it's actually a first year course called Functional Programming. So what is functional programming? Is it useful as in functional? Not quite. In short, functional programming means programming with functions, like those in mathematics. And to make it really look like math, some of the programming constructs that we normally use, like for loops and while loops, are banned in functional programming, making these programs fairly different from those that we're used to. Still confused? No worries. That's why you're here. Today, I will show you the basics and potentially shed some light on its usefulness, quirkiness, elegance, and what makes it the most interesting course in Oxford. You're gonna see lots of examples of functional programs, which I will broadly divide into two groups, which are functions that deal with numbers and functions that deal with lists. With these examples, my plan is to complement existing videos on YouTube, which focuses more on the theoretical aspect of things. So no for loops, no while loops. But we want to tell our computers to do something again and again because that's important. So what can we use instead? The answer is recursion. For those of you who are not familiar with recursion, it means functions that call themselves in their function body. For example, here's a recursive function that computes the factorial. And by the way, the factorial of n, which is written as n exclamation mark, where n is a natural number, means the product of n minus 1 all the way down to 1. And 0 factorial is defined to be 1. Well, it kind of makes sense actually. So back to the code, the factorial function is split into two cases using an if statement. First is the base case. We state that factorial of 0 is 1 by asking the function to return 1 when n is 0. And then comes the recursive case. When n is greater than 0, we ask the function to return n times whatever factorial of n minus 1 is. And that's all you really need. So right now we will look at an example for the calculation of factorial of 4 by calling fact4. So we know that 4 is not 0, so that's why we return 4 times fact of 3. But we don't know what fact 3 is, so therefore we do another call to fact, but with 3 as input. So this time 3 is not 0 either, so we return 3 times fact 2. And similarly, fact 2 equals 2 times fact 1, and fact 1 equals 1 times fact 0. But this time is different because our code says if n is 0, we return 1. So 1 is returned, there's no more recursive calls, and therefore we can calculate the answer, which is 24. Before we wrap this up, I would just like to take some time to motivate the use of recursion and functional programming over the normal for loop or while loop approach. When we look back, the mathematical definition of factorial of n equals to n times n minus 1 all the way down to 1, you'll find that it's a little bit imprecise. Specifically, it didn't really say what factorial of 0 should be. So in fact, the formal definition would be that 0 factorial is 1 and n factorial is equal to n times n minus 1 factorial otherwise, which actually says the same thing as our recursive function. So that's the first advantage of using recursion and functional programming, that is, the code we write aligns more closely to the mathematical definitions. I know some of you are scared when you see recursion, but trust me, this is as difficult as it gets in this video, though it's true that there's a lot to talk about for recursion, so if you're interested, let me know down in the comment section and I might make another video on it. So without you noticing, we have already written our first functional program. However, I would like to stress that functional programming is a lot more than just recursion, which is something that I want to convince you by the end of the video. And with that said, I think it's a good time to move on to the second example, where we sum all the elements of a list. Just to be clear, sum of 1, 2, 3, 4, 5 would be 15. And I'm sure most of you will know how to implement this function using a for loop. Here's what it might look like. And we take a little note that the sum of the empty list is 0. Okay, so we'll try to do the same using functional programming. So similar to what we did in the factorial example, we'll split it into two cases. However, this time, we'll split it into the empty list case and the non-empty list case. And now let's figure out what we want to do within the if clauses. It's a good time to go back to the title screen. Notice that functional programming is not just about banning loops. It is also about banning mutable variables. What does it mean? It means once variables are initialized, their value cannot be changed. We will motivate why this is a good idea in the next example, but for now, let's just set this rule. So what's the implication? It means there's not much we can do within the if clauses. What we should only do is to prepare for the output, the stuff that we want to return. So we begin simply by writing a return statement. So for the empty list case, we obviously return 0 by definition. The other case is a bit more tricky. We observe that every non-empty list has a first element, which is indexed 0 by the way. And if we can obtain the rest of the list without the first element using the syntax 1: in Python. So under the spirit of recursion, we should handle the first element, then use the recursive call to handle the rest. Specifically, we should sum the first element with the result of the recursive call on the rest of the list, and that's it. Okay, let's test our function with an example. We want to sum all elements of the list 4, 7, and 5. The recursive clause tells us that we should return 4 plus the sum of the list with 7 and 5 in it, which gives 7 plus the sum of the list with only 5 in it, and that gives 5 plus the sum of the empty list, which is 0 by the if clause. So with no more recursive calls to handle, we happily return 16. So far so good. Time for another example. This time, we concern ourselves with a function that I name doubleList, which doubles every element of the given list. A simple example would be doubleList of 1, 2, 3 gives a new list with 2, 4, 6. Similar to our previous example, we split our code into two cases. The case where the list is empty, which is the base case, and the case where the list is non-empty, which is the recursive case. And as previously discussed, there's nothing too much we can do because we can't have mutable variables, so what we can do is just a return statement. But what's different in this example compared to the previous two is that we want to return a list instead of a number. When the input is empty, there's nothing to double, so we return the empty list. Otherwise, there is a first element in the list, we double that element, and add it in front of the result of the recursive call on the rest of the list. Note that the plus sign here means list concatenation. We are combining the singleton list with the first elements times 2 with the result of the recursive call, which itself gives a list. A running example of the doubleList function is presented on the screen. Very similar to the first two examples, we first use the else clause multiple times until we reach the case where the list is empty. That's when there are no more recursive calls, and finally we consolidate our answer. Again, note that the plus sign here means combining two lists as opposed to addition. Now, after we have a good idea on how this function works, it is a good time to explain the rationale behind not allowing the use of mutable variables. Let's imagine you are a part of a software team. Your colleague wrote this function called doubleList and tells everyone that it is a function that doubles every element of a list, and everyone in the team can use it. And you are a user of the function, not the writer, knowing only the specification of the function from your colleague, a pretty informal one in fact, but not bothered to look into the source code. And yeah, this always happens because the source code is often more complicated than this toy example. And you start writing your code, initializing a variable called a's, and assign b's to be the result of calling doubleList with a's as an argument. Only to notice what your colleague said is a bit ambiguous. They specify this function doubles every element of the list, but it could mean one of two things. Either a copy of the original list is created with all its elements doubled, leaving a's unchanged. Or A is modified, and now both A's and B's now point to the same list, while the original contents of A's are gone. If the code is written in a conventional programming setting, you better ask your colleague which one they meant. Because suppose you want to modify A's after the function call, you want to know whether that would affect B's as well. In the former approach, it won't, but in the latter approach, it will. But if your team is lucky enough to have that functional programming, this won't be an issue because the latter approach is impossible because it involves mutating A's. The functionality of doubleList is clearer in a functional programming setting because of the limitations imposed by functional programming. We have done a lot, so let's do a little consolidation. We established that functional programming involves two basic principles: that we do not allow loops and we do not allow mutable variables. And we motivated some reasons behind these two seemingly bizarre rules. That is to bring programming much more closer to mathematics, and as a result, gives much more robust code which are less prone to errors and more interpretable, at least by mathematicians. Therefore, functional programming is sometimes used in back-end systems where you do not want any errors happening because they are very expensive to fix. Currently, functional programming is used by a handful of notable companies. To illustrate the final point I want to make in this video, let's start with a little exercise. I would like you to write a function that negates every element of the list, which I will call negateList. For example, negateList of 1, 2, 3 is -1, -2, and -3. Make sure to reference our previous example, doubleList, because it's reasonably similar. Now pause the video and try to work it out. Only two small changes are needed to convert doubleList into negateList. First, we change the name of the function, and don't forget to change the recursive call as well. Second, we change what we are going to do on the first element of the list. Instead of multiplying it by 2, we simply negate it. Job done. The similarity between doubleList and negateList makes people think if we can generalize this idea. And yes, we can. We task ourselves to write a function that applies an arbitrary function, which we will call f, to every element of a list. Conventionally, this function that does this is called the map function, and it takes two arguments, f, which is the function to apply, and x's, the list. We change the recursive call accordingly, and instead of negating the first element of the list, we apply f to it. I believe that the map function is not hard to write, but most people failed to appreciate the intricacies and implications of it. So let's dive in deeper. Starting with an example, we write a function that I call double, that doubles a single number. We then consider map double list 1, 2, 3, and it effectively performs double on all elements 1, 2, and 3 respectively. And we end up with a list with 2, 4, and 6. Generalizing this idea, it is easy to see that map double x's is equal to double list x's for all reasonable lists x's. And if we observe that both sides of the equal sign contain x's, so let's ignore it. And we can say, more or less, map double equals to double list. So the lesson learned is that we can write our doubleList function with map, which converts the function double that acts on a single number into one that acts on lists of numbers. Very similarly, instead of writing the negateList function, like what we did before with if statements and handling recursion ourselves, we could have written a negate function that negates a single number and extended it using map to handle lists of numbers. And we can write the equation negateList equals to map negate. I think it is very interesting that we're able to use this mathematical equality sign on computer functions. That's because of all our hard work to make programming mathematical, and our hard work pays off here. That is our realization that map can implement doubleList and negateList from double and negate, and similarly, map can create many other functions from existing ones. Besides, it is important to note that functions can take other functions as arguments. I'm sure that some of you didn't know you can do that. Map takes a function f as an argument, making map something called a higher order function. Roughly speaking, with this newfound power, it is widely believed that functional programming and conventional programming are comparable in terms of computing power. We can write very peculiar functions, like this function g that I'm writing here. It accepts an argument x and returns x applied to itself. So what is g applied to g? It is gg, 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 and goes on and on. Do you get it? Oh well, that's not the main point, so it's not important. The study of these functions is called Lambda calculus, and I promise it's very fun. If that catches your eye, feel free to learn more by watching this YouTube video by Computerphile. Link is in the description. Now before I end this video, I really would like you to look at a few more examples of functional programs. However, instead of me talking through it, it is much more interesting for you to work on them hands-on. Therefore, there will be exercises for you. Don't worry, I will give you hints and show you the answers at the end. Your first task will be to write a functional program that gives the product of all elements of a list. A very big hint is to reference the sum function that we talked about earlier. So I'll give you some time to work on it. So a few changes are needed. First of all, change the function name from sum to product or anything meaningful. Change the plus sign into a multiplication sign. And one last thing that most people forget is that when the list is empty, we should return 1 instead of 0. Notice how if you didn't change it, product of all lists will be 0. Or if you learn enough mathematics, a more formal way to explain it would be 0 is the unit of addition, while 1 is the unit of multiplication. And we're all set. So for the next question, we're asked to write a function that gives the length of a list, of course using functional programming. I advise you to start with the framework that we have been using throughout the whole video. That is to split it into two cases using an if statement. It's the case where the list is empty and the case where it is not. Within each clause, we simply write a return statement. Now pause the video and try to fill it in. If you get stuck, resume the video for hints. Now let's start with filling in the empty case. The hint would be to think about what should be returned when the list is empty. When the list is empty, the length for the list is 0. That's why we return 0. And for the non-empty case, we should focus on thinking about how to arrive at the final answer given the result of the recursive call. Observing that the recursive call is on a list that is 1 shorter than x is, we simply add 1 to the recursive call result. And for the last question, we are asked to write a function that gives a boolean of whether the list is odd. That means if we give a list with an odd number of elements in it, for example 3, we should give true. While if we give it a list with an even number of elements in it, for example, if the list is empty, or let's say length 2, it should give false. We start with our usual framework, like in question 2, and I'll give you some time to work on it. A reminder that this time we are returning a boolean, that is a true or false value. So this question is indeed a bit tricky and is a bit challenging for most of my students. However, to finish the empty list case, we don't need to think too much at all. We just need to think about what we should return when the list is empty. When the list is empty, the length is 0, which is an even number. That's why we return false. And for the non-empty case, you think about how to arrive at the final answer given the result of the recursive call. So put it into the context of this function. The recursive call result tells us whether the list without the first element has length even or odd. We observe that if the list without the first element has length odd, the whole list will have length even. And if the list without the first element has length even, then the whole list will have length odd. So if the recursive call result returns false, we return true. And if the recursive call result gives true, we give false, which is the not function. And we're done. That's the last exercise. So take your time to sink it in. If you are interested in learning more about functional programming, other than checking out the video on Lambda calculus I mentioned, you may also check out these 2 videos. Their links are in the description. The last video is in Chinese. However, I think the script is well written and high quality English subtitles are available. If you are very dedicated and more into books, here's a book written by Richard Bird that covers the basics of a common functional programming language called Haskell. And here's a piece of notes prepared by University of Cambridge on functional programming. The link is also in the description. You may have noticed that functional programming is, I won't say similar, but related to mathematics. I would like to end this video by reminding you that mathematics is an integral part of computer science. Thanks for watching. And if you have watched the whole video, chances are you are interested in computer science and don't mind the math that comes with it.